Okay, let's jump straight into our mission briefing. Welcome to today's explainer. We are taking on the ultimate engineering challenge, upgrading a collapsing data grid by designing an architecture that can actually withstand massive, enterprise-level scale. We're not talking about a simple blog here. We're talking about a system being pushed to its absolute brink.
The stakes are incredibly high for this one. We have to engineer a system capable of processing a crushing 5 million reads every single hour. Literally, if our architecture isn't pixel perfect, a load this heavy will cause the system to flatline almost instantly.
And, as if that wasn't enough, simultaneously, we're dealing with a relentless data stream of 500,000 writes per hour. That's 500,000 complex updates, inserts, and modifications happening while millions of users are desperately trying to read from the exact same system.
So, the million-dollar question, well, I guess literally the $5 million question, is how do you actually survive 5 million reads and 500K writes an hour? A traditional monolithic database where one single data store handles absolutely everything will just instantly short-circuit under this kind of concurrent load. You're going to hit lock contention, thread starvation, and catastrophic timeouts. We need to completely rethink our approach from the ground up.
Section 1. Assembling the Polyglot Crew.
We aren't just relying on one database anymore. We're assembling an elite crew of specialized data stores. It's this brilliant concept called Polyglot Persistence. Basically, it means we stop looking for a single silver bullet database. Instead, we use the absolute best tool for each specific architectural job. We break that monolith apart and distribute the work to the specialists.
Let's look at who's on our crew. SQL Server is our vault, locking down our core relational data and ensuring strict transactional integrity. Redis acts as our courier, an ultra-fast, in-memory distributed cache. Elasticsearch is our oracle, which takes the heavy listing of complex text searches right off the main database. And finally, Amazon DynamoDB gives us the network, a globally distributed, highly available NoSQL database. Together, they form an unstoppable grid.
Section 2. Splitting reads and writes. Now that we have our crew, we need a strategy to route these massive traffic flows without causing a systemic bottleneck. If reads and writes are constantly colliding, we fail. This is where we introduce the CQRS pattern, Command Query Responsibility Segregation. This means we completely separate our read models from our write models. In a traditional system, reads and writes share the same model, which inevitably leads to data mismatches and severe lock contention. CQRS prevents them from locking each other out.
So here's exactly how CQRS works in practice. Our write paths, or commands, execute the strict, complex business rules. Think of a hotel booking system making absolutely sure a room isn't double booked. Meanwhile, our read paths, or queries, just bypass all that heavy domain logic. They just instantly retrieve pre-shaped data transfer objects, or DTOs, right to the screen.
Section 3. Optimizing Entity Framework Core.
Let's move down to the code level to see the cybernetic wiring connecting our application to these databases. To handle those 5 million reads, we have to strip away every single ounce of unnecessary overhead in EF Core. The framework is incredibly powerful, but out of the box, it tracks a lot of information we just don't need for high-speed reads. The absolute crucial point for read-heavy operations is using as-no tracking. When EF Core runs a standard query, it creates snapshots of your data so it can track changes. That eats up memory and CPU. For our read-only queries, we don't care about updates, so we literally tell EF Core, hey, don't track this.
By combining as-no tracking with DB context pooling, which lets us reuse database connection instances instead of constantly building new ones, and precise link filtering, we ensure our queries return data with absolute minimal latency. We also heavily avoid those nasty N+1 queries, where the system accidentally fires off hundreds of individual database calls when just one would have done the job.
But what about the 500,000 writes? We turbocharge those using execute update and execute delete. Look, if you wanted to give 1,000 employees a raise, the old way required loading all 1,000 records into memory, updating them, and sending them back. It was painfully slow. Introduced in recent versions of EF Core, these methods are total game changers. They let us execute bulk updates in a single database round trip without loading a single piece of data into client memory. It directly translates your C# code into a highly efficient SQL update statement, completely bypassing the heavy change tracking machinery.
Section 4. Neon Fast Distributed Caching.
Even with highly optimized queries and separate write paths, we have to deflect as much traffic as possible away from the main databases. This is where distributed caching comes in. But caching at this scale is dangerous. We have to architect carefully to avoid something called a cache stampede. Imagine an incredibly popular piece of data expires from the cache. Suddenly, thousands of concurrent requests all realize the cache is empty at the exact same millisecond, and they all stampede the primary database to recalculate it. That will trip your system alarms instantly. To build our neon-fast caching layer and mitigate these risks, we use Redis. By leveraging the StackExchange.Redis high-performance multiplex client, we can handle multiple concurrent threads over shared connections hyper-efficiently. This creates a blazing fast, distributed memory layer that easily survives individual app server restarts and shields our relational vault from the heavy read load.
Section 5. Resiliency in the grid.
Our high-scale grid must be able to self-heal. Let's be real, when you rely on an elite crew of distributed databases, a remote dependency will inevitably fail. Networks glitch, servers reboot. We have to plan for it. Instead of endlessly retrying a dead connection and exhausting all our application threads, we implement the circuit breaker pattern. It acts exactly like the electrical breaker in your house. If the grid surges, it trips the breaker to save the house from burning down.
The circuit breaker operates in 3 states. Closed means everything is normal, requests are flowing. If failures spike, it snaps to open, instantly blocking requests and throwing a fast exception so we don't tie up resources. After a timeout, it transitions to half open, allowing a few test requests through to see if the database has recovered. Using a .NET library like Poly, our system intelligently manages these transitions. And here's how we combine these resilient strategies. We pair the circuit breaker with fallback policies. So if the primary database is open and rejecting requests, the fallback silently serves up slightly older cache data from Redis. By layering circuit breakers, fallbacks, timeouts, and retries, our application gracefully degrades instead of taking down the entire grid.
We've covered massive ground today, from the raw scale of millions of operations to polyglot persistence, CQRS, EF core optimization, and resilient circuit breakers. As you look at your own architecture, consider where these high-scale specialists could relieve your biggest bottlenecks. Which part of your data grid needs a polyglot upgrade first? Think about it. Thanks for joining me on this explainer, and I'll catch you on the next